Welcome to solverfy.
So in this case, we have two 20mm steel plates welded onto a rolled S section as shown. So we have these plates welded onto this I-beam or an S section. Determine the area moments and everything, radii gyration and everything about the centroid here, which is going to be at the centroid of the I-beam because these things are symmetric. They're symmetrically welded about this axis, and they're symmetric about this axis. So we can look up some values for, these are just rectangles, so we can calculate those, but for this section here we have to look it up. We get that the distance between its top and its bottom is 305 millimeters. And the area is 6,010 millimeters squared. The area moment about its centroidal x-axis, which is actually the centroidal x-axis of the whole section, is 90.3 times 10 to the 6th millimeters to the 4th, and about the y-axis, which is also the y-axis of the centroidal y-axis of the whole section, is 3.88 times 10 to the 6th millimeters to the 4th. The total area is 2 times B times H, since we have two plates, and plus A2, the area of this guy. Now we can start calculating the area moments for these plates. So that's the area moment about the centroid. Plus, for the x-axis, we need to use a parallel axis theorem, plus its area times d over 2 gets us up to the top of this or to the bottom of this plate, and then we need to go h over 2 to get to the middle of the plate. So we get d plus h over 2 squared. The centroidal y-axis for this whole cross-section goes through the centroidal y-axis for the plates, and so that just becomes 1/12 hb cubed. Now we can look at this. We have this because, and we know that it's the centroidal axes of the whole cross section goes through the centroidal axes of this subcomponent. So we can just plug those values in from here. We have two plates, again because of symmetry, where you can see that they're going to have the same values. And so we get two of those, and so we get about 260 times 10 to the 6th millimeters to the 4th for the area moment about the x-axis, and about 17.5 times 10 to the 6th millimeters to the 4th about the y-axis. We can see that it's much bigger about the x-axis than the y because we have much more material away from the x-axis than we do from the y-axis. So that makes sense. Again, we have the cross-sectional area, and so we can find the radii of gyration, and about the x-axis is 144.6 millimeters, and about the y-axis it's 37.59 millimeters.